So, now let us look at relativistic field. I will not start with this in my field theory lectures, but we need to do this. I mean, of course, we will QD, quantum electrodynamics will all be relativistic fields. So, we have four variables space time, no. So, space time is t and x, the contravariant and the covariant is d by dx, d by dt. Okay. So, instead of writing dt dx, we write d for x, okay, space time together, and this is a Lagrangian density, and we know this variable, this covariant derivative, no, d phi dx. Okay. I will not delve into it because this is a huge topic. So, we will just, well, I think we will do bit more when we get to that, but I am just going to state the results. So, the equation of motion is this partial L partial phi, this is same as before, but those time derivative and space derivative are combined here. Well, d0 is dt partial dt, and d other ones like dk, space derivatives are dk. Okay. So, so 0 is time and the 1, 2, 3 are space. Okay. They are combined here. So, if you write t and x separately, we will get back the same equation. Example, now this is for phi 4, this is the for free particle, okay, this is the Lagrangian for a free particle. Okay. So, this is the kinetic energy term, but remember it has both d by dt and d by dx square in this. So, if you expand this one, this is d by dt of phi squared minus grad phi squared. Okay. That is the first term. Why minus sign? Because this is a relativistic field. So, you get a minus sign, no. I mean, this part I do not want to belabor on this, but invariant thing is t squared minus x squared, not t squared plus x squared. Okay. This minus sign is product of contravariant and covariant vectors. Okay. So, the minus sign will come here and minus half m squared phi squared. This is a Lagrangian density for a relativistic free particle. This is a free particle with mass m. This in fact is mass m. Okay. So, so we get I can do the same algebra. Okay. Let us do it here. So, if I do dl by d phi, what will I get? Minus m squared phi, right, this one. Here I get d by dt of partial L partial d dt phi. So, this term will give us, okay. So, this the second term will be, let me write this term. So, partial t. So, this is basically this term derivative. So, half and 2 will cancel. So, dt d phi. So, this is this term double derivative in time. The next term is this one grad phi squared. So, I get d mu, well, the space derivative, let us look at x derivative, d by dx of partial L partial dx phi, this one. Well, same idea except there is a minus sign there. So, I get minus dx square phi, okay, and dxx, double derivative with x, plug that in here, we will get this equation. So, this is the plus sign, well, sorry, these are all are minus sign, no? These also minus sign, these also minus sign, these also minus sign. Okay. So, how do I get minus plus sign? Let me just check. So, 0 equal to that. So, this is a minus sign here, minus phi squared, this is minus sign and this is plus sign because this is a plus. I take a this is a minus sign here. So, there is a minus sign, well, there is a minus sign here, there is minus sign here, no, minus. So, the minus sign here and minus sign here as well. So, minus minus becomes plus. Okay. So, look here this equation is written like that, minus m squared. So, this has d by dt of partial dt phi, okay, and then with there is a minus sign, and same thing with x. Okay. So, there is a minus sign here, so the minus is equal to plus, plug that in. Okay. This I have taken into the left hand side, this is minus m squared. So, go to the left is plus m squared, this is minus d by dt, so that becomes plus, and this is plus, it becomes minus. So, this is the equation. Okay. So, we get dt squared minus Laplacian squared plus m squared phi is 0. Okay. For m equal to 0, we get the wave equation like classical electromagnetic waves, but m not equal to 0 is a massive field with mass. Okay. So, in fact, this object is written as Laplacian, this one. Okay. Shorthand in using relativistic fields, this square equal to dt squared minus Laplacian squared. Okay. So, we will encounter this. This is what this is one of the important equation for field theory. Of course, this is a free particle, but then we need to put interactions. Okay. So, interaction once you put in, it will become 5-4 theory. Okay. Thus, you might have heard 5-4 theory, 5-6 theory. So, there will be interactions.